little question in itself. Okay, so, oh, by the way, since I'm doing this, I need you guys to like participate and like actually like put in the answers for these questions, because I mean, we just saw it for the first time last time. So I'm hoping if you see it now, it's going to make it easier. Okay, so this question was embedded in question number 3 for your lecture quiz, right? And I say about, there was a lot of people forgot this part. You just use your volumes that I gave you, but that's not what you have to do if it's going to be neutralized. You have to figure out the volume. So this question here, and why I'm starting this question, is you can see that this question isn't actually an ice table, and it's not really even a 229 question. This is a 219 question, right? If you look at this question right here, by the way, if you can solve this, solve it, put it in the chat. If you look at this question here, there's a molarity and a volume and another molarity, right? We can just stoichiometry. That's it. So you just use your stoichiometry to solve this problem, and then you can get to your volume. Okay, so try this question, and then we're gonna go over it. So I'll give you like, by the way, I'm just gonna use HA because it seems that people don't like HA, so I want to get used to it. HA just means any weak acid. Pick one. I always say use HF. Use HF. Looks just like HA. Okay, so do that, and then we're gonna go over it. I'll give you like a minute. I'll give you a minute, and then we're gonna go over this. All right. So yes. So I have just some like extra things just showing you this, but this is just stoichiometry. And so when you do this, you literally just do your mole ratio. It's 1:1, and you up with 50 milliliters. So again, this right here, a lot of people miss this on question 3. A lot, just forgot, right? Just forgot to do this part on question 3. So you need to do this for question 3. And if you're like, where? Well, we'll see if we get it. And so 50 milliliters. Okay, so another one. Okay, so we have a weak acid with a strong base. I want to know the pH before the titration, right? And I'm giving you the Ka, right? So how do we find the initial pH? So if we're going to find the initial pH, that means nothing's happened. Nothing has happened yet. So we just worry about this, right? This doesn't matter because it's the initial pH, right? And by the way, I'm going to keep with the same question, the same problem. So you're going to see, you shouldn't have to rewrite the problems. I'm going to try and keep the same problem the entire time. Okay, so since this is the initial pH, that means all we have is a weak acid. So then this is just going to be an ice table of a weak acid, right? So we're going to determine the pH from an ice table of using a weak acid equilibrium. Okay, so try this one, and then I'm going to give you 3 minutes, and then we're going to go over it. So try this one. Okay, so we have a few of these. Yeah, so this is just a weak acid ice table, right? So this is just a straight ice table. This is no moles table needed. Again, because all we have is a weak acid, we haven't added anything to it, right? And so when we do this, we're just gonna have, should be x squared over 1, which is a nice easy one. I'm just gonna assume x is small here. And it should work because of my concentration difference is 5. We get our x, negative log of 2.5. Right, and again, just for a little sig figs, this was all over the place on the quiz too, right? 3 here, because there's 3 here, right? We look after the decimal point with this. All right, so we've done a few of these now. Okay, so I also wanted to show you the shortcut. So with Henderson-Hasselbalch, you don't necessarily have to go to molarity. I kind of like hinted at this last time, but because we're dividing both of them by volume, they just cancel out anyway. So, and since they cancel out anyway, you can do Henderson-Hasselbalch with moles. So that should kind of save you your last step at sometimes. So you just do moles of your conjugate base over moles of your weak acid. And again, that's because since it's a ratio and you're dividing them both by volume anyway, so you don't necessarily need your volume again, but this will only work in your Henderson-Hasselbalch. This doesn't work in an ice table, just in Henderson-Hasselbalch. Okay, same problem. Now this time, I want you to calculate the pH after 10 milliliters of NaOH was added. This is very similar to number 1. It's really similar to one of the questions on the lecture quiz. Very similar. Okay, so this time we have to figure out, we have to use a mole table. Now the reason we have to use a mole table is because we need to figure out, we have our moles of our HA, and from here we can get our moles of our NaOH. Remember, molarity times liters equals moles. We need to figure out how many moles of base are reacting with our weak acid. So that's why we have to do a mole table. So the reason and when you have to do a mole table is when you add something to something else. That's when you do your mole table. When you're adding something to something else, you got to do a mole table. So first thing first, we have to find our moles, right? And you have to find both moles. Okay, so most people did this part right. You found your moles right. Not hard. Now it's time for the moles table. So a lot of people did the moles table incorrectly. Okay, so I'm going to give you a minute. I'll give you 3 minutes again to solve this one, and then we're going to do it together. Very similar to the one that's on the lecture checkup quiz yesterday. So I'll give you 3 minutes and then we'll go over this. Okay, let's go over this one. So for your moles table, here's the moles we started with of our HA. Here's the moles of NaOH. So we're adding this many NaOH moles to that moles of HA. So HA is going to go down that much. So HA is going to go down by this amount, right? And the reason it's going to go down by that amount is because the base is going to react with the acid, right? So here's the amount it goes down by. And then we're left with, and then of course, if this is going to go down by here, right? And again, I'm going to just draw a little Le Chatelier's. If you add this, this goes down, right? And Le Chatelier's will go over here, which will make this Na go up. Or you could just do A minus, either or. I kind of went back and forth on this. Okay, so now this is our new moles. And if you look here, this is where that new little shortcut I just taught you can be used. So we have HA, our weak acid, and A minus, our weak base. This is a buffer. We can use Henderson-Hasselbalch, right? And because Henderson-Hasselbalch, I just told you, has volume, both of the volumes, we can just ignore the molarities and just put the moles straight into Henderson-Hasselbalch. And so when you do that, you get 4.398. So it's not as, it takes out that one extra step with the molarity. You can do it with the molarity. You're going to get the exact same answer, but you don't have to do it with the molarity when you're using Henderson-Hasselbalch. And remember, the only time you can use Henderson-Hasselbalch is when you have a weak acid and its conjugate base, right? So I could have just written this like A minus, right? So just think of like, this is HF and this is F minus, right? That's a buffer. Okay, now, what about after I add 25 milliliters? Okay, so now for this one, very similar, try this one and then we're all gonna go over this together. I'll just, actually, I'm not even gonna find the moles for you this time. I'm gonna have you find your moles for this one. Okay, try this one and then we're gonna go over it together. Okay, I'm getting a few answers from the chat. So again, how are we going to attempt this problem? So here we are with our weak acid, and there we are with our strong base. So we're adding something to it. So we're going to have to do a moles table, right? So that should be your clue. I'm going to have to do a moles table because I'm adding something to it, right? And so therefore you got to find the moles, right? So we got to find our moles. So we know we're going to have to do a moles table because we're adding something to something else. Got to do a moles table. So we figure out our moles. Nice. Okay. Then here's the reaction that's happening. Our acid plus our weak acid plus our base. And again, what's going to happen is here's our acid. That's what's in the beaker. We're going to add this NaOH to our acid. So here's what we have initially. So we're going to subtract this amount of NaOH. That's what we're going to go down by because that's what we're adding. And this is why we have to do that moles table. And again, our NaA will go up, right? Because if we add this, it's going to shift that way, Le Chatelier's, right? And so then, interesting here, look, we have the exact same amount of each of these. This is a question very similar to your lecture quiz, right? We have the same exact amount of HA and Na. Okay. Oh, for the lecture quiz, I didn't give you KA, but it's open note and open book and open everything. So you just look it up, right? So if I don't give it to you, it's open everything. All you have to do is look it up. I gave you the identity and it was the same one we used in lecture. Okay, so now for the Henderson-Hasselbalch, we just, again, we have the same amount. And so then this ends up being 0. And this is when pH equals pKa, right? That's our half equivalence point. So this is a question very similar to our, let me just go back for a second. So this is very similar to our, and I guess I forgot to give you the pKa on here. The pKa was 5. Yeah, my bad. On here, I had to give you the pKa. On your quiz, I gave you, you could have just looked it up. But here, since this is HA, I would have had to tell you the pKa is 5 in this place. Okay, so I think you could have figured out because there was Ka like 4 problems ago, so you could have figured this out because I had the Ka there from before. Okay. Okay, so the reason for this, remember this, I'm going to show you, this is our shortcut. So because we have HA, which is our weak acid, and we have A-, which is our weak base. This makes it a buffer. Because it's a buffer, that's why we can use Henderson-Hasselbalch for this. Now, remember with Henderson-Hasselbalch, I just taught you the shortcut. You don't have to find the molarity. And you don't have to do an ice table because it's a buffer. You can do an ice table, but who wants to do all that work? But you could. Right? But if it's a buffer, you do not need to do an ice table. You can use Henderson-Hasselbalch, which makes our life easier. But you could do an ice table. You just don't have to. And again, the reason you don't have to do an ice table here is because it's a buffer. It's a shortcut. Okay, now calculate the pH of a solution at the equivalence point. That sounds like number 3 from your lecture quiz, doesn't it? Okay, let's try this one. I'm going to give you a minute, and then we're going to go over this one together. I'm going to interrupt because Michael had an excellent question. For the NaOH, there's not a volume. There isn't a volume, but from the information given, we can calculate our volume needed to get to our equivalence point, right? So this is using part of the first question with this one, right? Because look, we have a molarity here and we have a molarity here. We just need to figure out our volume of our NaOH. It's just a stoichiometry problem, right? So we can do that. And this is the part, like, again, the majority of the people missed on their lecture quiz on part 3, on question 3. So I'll give you another minute or two to finish this one. So let's go over this. All right, so we need to figure out our moles of both, right? And now from our first question, we've figured out we got 50 milliliters, right? And again, how did we get that? So I'm just gonna do it, I'll just do it really, really fast. So if we have 20 milliliters, that's 10, oh gosh, okay. Maybe I won't do it that fast. I get 3 liters. And then we have 1 mole over HA, so 1 mole of HA in 1 liter. Our mole ratio, we have our molarity of our NaOH, which is 0.4 moles NaOH per 1 liter, right? When you do that, you end up with, that's where we got that volume, right? And again, this piece right here is what a lot of people did not do on that lecture quiz. You have to find that volume, right? And so then you can find your moles, right? So after you find that volume, then you can find your moles.
Professor,
Yes.
I think it would have been 2 times 10 to the negative 2, not to the negative 3.
Oh, for this?
Yeah, when you were writing it out, you put negative 3 instead of negative 2.
No, it's negative 3 because you move it over 3. 20. Oh, sorry, that was supposed to say 20 times 10 to the negative 3. Did I forget the 0? My bad.
Yeah, sorry about that.
Yeah, no, thank you. Yeah, if I put 2 times 10 to the negative 3, I'm sorry, I must have forgot the 0. I meant 20 times 10 to the negative 3. My bad. That's just my fast way of converting to liters. I just multiply my milliliters times 10 to the negative 3. So my apology for forgetting a 0. That's a big forget. Okay, so now we have to do a mole table. Why do we have to do a mole table? Because we're adding something to something else. So we got to do a mole table. And in this case, when we do our mole table, we happen to have the exact same number of moles of both, which 2 ways you could have known that was, number 1, if you didn't calculate this, let's say I didn't calculate that. That's okay, you know what your answer is. How do I know what my answer is without even calculating this? Because the definition of equivalence point. The definition of equivalence point is literally when the moles of your acid equal the moles of your base. So if this is at equivalence point, this also equals my moles of my base. So let's say you didn't want to do that stoichiometry problem I just did. You don't have to. the definition of equivalence point is that these two are the same, right? And so we just proved it by calculating it, but you can literally just say, oh, we're at the equivalence point, moles are the same. That would have been a completely fine way to find your moles. Okay, so now, when we do this part, we're going to subtract 0.02 because we're going to add that, right? That's how many moles of base we're adding to our acid. So we have we've used all of our NaOH and our weak acid, but we're still going to have Le Chatelier's, right? If we add this, it's still going to shift over here by that amount. So our A- is still going to go up by that amount. And so now all we have left is this A-, right? So all we have left is a conjugate base in this case. And if all we have left is our conjugate base, this is going to be a weak base equilibrium problem, right? Because what we're going to do is this base is all that's left. So it's going to be in water. So it's going to react with water to make, right? That's what's going to happen to our A- when we put it in our water. So now, since it's a weak base equilibrium problem, we have to find the molarity because now we need to do an ice table, right? Any of our equilibrium problems have to have ice tables. So therefore, we have to find the molarity. And again, this is where a lot of people did not do this piece. Now you have to find the volume. In this case, you needed to get that calculation for the 50 milliliters plus 20 milliliters, right? So in this case, with your molarity, you have to find the total volume. And again, it's just saying that at the equivalence point, the solution will only contain the salt, and it's going to be a weak base, so it's a weak base equilibrium problem. Okay, so quick little thing. If you have a weak base, that means you need to use Kb. Weak base means you need to use Kb. I told you here was our Ka in the very first question, I think. So you got to find your Kb, right? So that's one little piece that you have to do, which this is one thing that a lot of people forgot. Who did get this far on question 3 forgot to find Kb, right? You just divide it by 10 to the negative 14th. Okay, then again, here's this part, this little piece that a lot of people forgot. You need to calculate this. This is that calculation, that stoichiometric calculation that I just did moderately incorrectly because I forgot the 0. But this 50 milliliters, you can also look back to the very first question we did today. That was the same one, right? That's where these 50 milliliters come from. You have to add that. Again, here's what a lot of people, they forgot to do this little calculation. So now we have our new molarity. Now we treat it like a weak base equilibrium question that we've now done a few times. Right? It's going to go down by x, up by x, up by x, minus x, minus x. We end up with x squared over our initial concentration. Assume x is small. And we get, again, POH. This is another little piece that a lot of people, mistakes they did. They just said that this was their answer. This is not the answer. This is the POH. You have to subtract 14 from it, right? So your answer is actually 9.228. And again, there are 3 significant figures here because this is 3 sigs and this is 3 sig figs and this is 3 sig figs. And when we do logs, we only look behind the decimal point. Okay, so this was the most commonly missed problem. So I want you to look at it here for a second and let me know if you have any questions. Any questions on this?
All is good.
We're all good with this one? Okay. Oops. One more. This wasn't on your lecture quiz, but I figured we'll just do one more for good measure. Okay, so now calculate the pH of the solution after 60 milliliters of NaOH was added. Okay, so I'm going to give you a minute to see if you can figure this one out without any help. So I'll give you like 2-3 minutes. Try this one, and then we're going to go over it. Yeah, the Ka on these are all the same. This is just the same problem. We're just going through adding stuff to it. So everything's the same to make it so you have less writing to do. Seeing a bunch of them come through in the chat. Okay, so let's go over this. Okay, so number one, let's just say I don't know that I'm over, that I have excess space. We'll just say I don't know that. We kind of do because we just did the other problem, but let's just say we don't know that. How do I know that we did that? Because we were at 50 milliliters last time. Now we're at 60, so we're definitely over. But let's say we don't, like we didn't have that problem before. Remember, whenever we're adding something to something else, we got to find our moles, number one. We got to figure out our moles. Whenever, in every single time, if it says titration or adding something to something else, you got to find your moles, right? Because every single time you got to do a mole table. When you see a titration, mole tables are kind of mandatory. So we have our moles of our NaOH, our moles of our HA. Remember, we're adding our NaOH to our HA, right? Because this is what we're starting with, and it says titrated with. That means that whatever's after this, this is what's being added to our acid. So therefore, we're going to go down by 0.240, but we can't go down by all 0.240. The reason is because at 0.2, we have no acid left, right? So we're adding all of this NaOH, but at 0.2, we don't have anything left. Right? So we can only go down by 0.02. We can't actually go down by the entire thing, which means that we have some extra base and a little conjugate base. Remember, our strong base is going to overwhelm our conjugate. So we can just pretend it doesn't even exist, right? Because our strong base is going to be so overwhelming to our weak base, right? So here's our moles table. We can just ignore this. And this is how much strong base we have. Now, with this one, we just solve it with the pH of a strong base, right? We can just take negative log of that and then subtract from 14. Don't forget to subtract from 14, right? Because if we take negative log of 0.004, that is the pOH, right? Not the pH. So here it is. Here's your ice table again. I'm sorry, your moles table again. And we know we're past our equivalence point. And so we have extra strong base. And so we just calculate our pH from our OH concentration. And again, we don't need this. And yes, we always ignore A minus here because of the huge difference between these, right? Only in the excess region do we ignore A minus, only in the excess region. How do we know that we're in excess? Because we have this left over, right? So we added our base to our acid, and now we have too much base. So we have extra base sitting in our beaker. And so now when we find it, so hold on, let me just go back here. Just looking at that last question. So this is our A minus right here, right? But this A minus is a weak base. Weak base. And it's so weak, right? And this is a strong base, so we can just ignore this, right? Okay. So now remember, when you do your pH, you have to use molarity. The only time you can leave it in moles here, which I think I said, like, I already assumed it was molarity, which it's not. The only time you can leave it in moles is if you're using Henderson-Hasselbalch, right? And if that confuses you, just never leave it in moles, always turning into molarity. With our molarity here, don't forget to add them. And when we do this, we get 1.3, and then we need to subtract because it's pOH. Again, don't forget to do this step right here, right? It's our molarity. The only time you cannot do molarity is if it's Henderson-Hasselbalch, right? If you have to use an ice table, or if you have to calculate pH, you have to do molarity. right? And all right, so let's see here. Okay, any questions on this piece that we have here? Question? There's our extra problems. Okay, so that's kind of reviewing everything we went through last class.